Genetic algorithm example. Let's check out a couple of problems that are better solved using genetic algorithms than other conventional optimization methods. The knapsack problem. Here, to make things easier, let us understand the process of finding an optimal solution with a genetic algorithm by the famous knapsack problem. If you haven't come across to this problem, let me introduce it for you. Let me introduce a version of this problem. Let's say you are going to spend a month in the wilderness. The only thing you are carrying is a backpack which can hold a maximum weight of 30 kilograms. Now you have different survival items, each having its own survival points. So your objective is to maximize the survival points. Here is the table giving details about each item. On this table we see the following items: a sleeping bag, a rope, a pocket knife, a torch, a bottle, and some glucose or food. Each one has its corresponding weight and the amount of survival points it represents. To solve this problem using genetic algorithms, our first step would be defining our population. So our population will contain individuals or chromosomes, each having their own set of genes. And for this example, we will set our chromosomes to be made of binary strings, where a 1 would mean that the following item is taken and 0 meaning that it is dropped. Now, a set of random chromosomes is considered as our initial population. Let us calculate fitness points for two random chromosomes. So for this problem, our chromosome will be considered as more fit when it contains more survival points. We can see in this table that the first chromosome includes the case where we travel with a sleeping bag, a torch, and a bottle. We get a total weight of 29 kilograms and a total of 28 survival points. Pretty neat. For the second chromosome, we're considering the case where we travel with a pocket knife, a torch, and a bottle, representing 16 kilograms of weight and a total of 23 survival points. Therefore, for this example, chromosome 1 is more fit than chromosome 2. Now, we can see Now we can select fit chromosomes from our population which can mate and create new offspring. In general, we should select the fit chromosomes and allow them to produce offspring, but that would lead to chromosomes that are more close one to another in a few next generation, and therefore be less diverse. Therefore, a very useful and general use technique is the roulette wheel selection method. Consider a wheel and let's divide that into m divisions, where m is the number of chromosomes in our population. The area occupied by each chromosome will be proportional to its fitness value. As we see on this table, the cumulative value of fitness of the individuals of our population has been normalized, and for each chromosome we have a corresponding probability proportional to its fitness. Based on these values, let us create a roulette wheel. So now this wheel is rotated and the region of wheel which comes in front of the fixed point is chosen as the parent. For the second parent, the same process is repeated. This way we keep on pairing chromosomes for reproduction and inheriting their chromosomes to the next generation. So, in this method we can get both our parents in one go. This method is known as stochastic universal selection method. So in this previous step, we have selected parent chromosomes that will be reproduced to generate new offspring. So in biological terms, crossover is nothing but reproduction. Now let us find the crossover of chromosome 1 and 4, which were selected in the previous step. Take a look at the following images. This is the most basic form of crossover, known as one-point crossover, where we select a random crossover point and the tails of both chromosomes are swapped to produce a new offspring. If you take two crossover points or more, then it will be called a multi-point crossover, which is shown in the next image. Now there is some change in the genes of children which makes them different from its parents. This process is known as mutation, which may be defined as a random perturbation in the offspring chromosome, which also promotes the idea of diversity in the population. A simple method, a mutation, is shown in the image below. For this chromosome, we are swapping the value of a random gene of a random chromosome from 1 to 0. So the entire process is summarized as shown in the figure. We keep on repeating these steps as a process. The offsprings produced are again validated using our fitness function. And if considered fit, then we will replace the less fit chromosomes from the population. But the question is, how will we get to know that we have reached our best possible solution? So basically, there are different determination conditions. Some are listed here. The first one is that there is no improvement in the population for over X iterations. This means that the solution of the algorithm has become static. A second option is that we have already predefined an absolute number of generations for our algorithm. This way, in a very large problem, we will set a maximum number of iterations and select the fittest solution of the last generation. Or maybe the algorithm will stop when our fitness function has reached a predefined value. Let's say it is very close to a desired value or beneath a threshold. Now, I suppose you have grasped the basic understanding of the genetic algorithm. The traveling salesman problem. This is a famous problem and has been efficiently adopted by many sales based companies as it is time saving and economical. This is also achieved using genetic algorithms. The problem is the following. Given a list of n cities, what is the shortest tour that visits each city exactly once and returns back to the starting city? One of the reasons why this is so famous is that it is easy to understand the problem but incredibly hard to solve. The figure in this slide illustrates some of the steps that a genetic algorithm used to arrive at what we think is the shortest distance 12,930 miles. This is the distance needed to visit all 48 continental US capitals. For this experiment, Google Maps was used to get actual roads and highways when computing the distance between cities. So now we see genetic algorithms are a very useful and powerful tool for optimization problems, and some of the applications for this type of algorithms are very conventional but also of great difficulty.